Hi guys, this is HSC Chemistry, the acidic environment, and the video on using indicators. In this video, we're just going to review some of the common ways that indicators are used in both natural systems and also in the chemical laboratory, and why this is an important thing for us to be studying. I've given you a list here, so the first thing to do is to have a look at this list of some of the key areas where pH is important. So the only reason that we would want to monitor is because there are certain key conditions that are important at particular pH values. Okay, and therefore if we want to maintain these pH values, then we need to know something about what values they are and why they're important. So by now you've actually had a look at some of these systems, natural water systems. We had a look at how buffers keep these together in a recent lesson. Swimming pools, which I'll have a look at a little bit later on. We've done some soil pH testing. We know that different types of plants require different soil pHs. We've looked at the fact that in places like the stomach, which is very acidic, or the blood, or in cells, there are certain values of pH that are important, and these need to be maintained within a certain balance. Also, things like certain types of fruit and vegetables will not ripen unless they have particular acidity levels or pH levels, and pH is also important in the cosmetics industry. We'll have a look at that in a little bit more detail when we study esters at the end of this topic. So in a chemical laboratory, there's a couple of different uses of indicators. The simplest, of course, is just a lot of solutions are colorless. And even those that are colored can not always be obvious what the salts are, but certainly for colorless solutions, we can't tell by looking at them what their nature is. So if we want to determine whether they're acidic, basic, or neutral, then indicators are one of the main areas, main tools that we can use to identify the pH of these solutions. But also, very importantly, and again you've had a look at this, is how we monitor acidity changes during volumetric analysis, so during a titration. And depending on whether we're looking at strong acid and a strong base, a strong acid versus a weak base, or a weak acid versus a strong base, this will determine the type of indicator that we use. And different indicators will be more or less relevant for each of these different types of titrations, and so therefore we'll need to determine which is the one that we're going to use in order to make sure that we can identify where the end point of the titration occurs. A specific example of where pH is important is in swimming pools. Obviously, we want to make sure that the acidity level in a swimming pool is reasonably neutral because we've got people swimming in it. So we want to make sure that neutrality remains, but we're also going to be adding certain chemicals to pool water because we want to make sure that we kill any bacteria. We don't want to encourage the growth of microorganisms in our pools. We want to make sure that they're clean and they're good for swimming. So one of the compounds that's used is sodium hypochlorite. When sodium hypochlorite is added to a swimming pool, it has a disinfecting action and it kills microbes. What it does though is it dissociates into sodium ions and OCl- ions, and this is the hypochlorite ion. Okay, this OCl- ion is our hypochlorite ion, this one. And when we put it in water, it acts as a Bronsted-Lowry base, accepts a proton from water molecules to produce the more unstable hypochlorous acid molecule, HOCl. And it also forms hydroxide ions, and you can see that in the equation that's just down the bottom here. Okay, so in this case, this is acting as a base, which means that our water molecule is acting as an acid. It's going to donate a proton in this direction, and so therefore this will be the conjugate acid, the hypochlorous acid, and this one, hydroxide, was going to be the conjugate base for water. So if you can start to think of all of these situations where we've got acid-base reactions in terms of their conjugate pairs, it's going to be easier for you to keep picking these up as we go along. So the reason that we add the sodium hypochlorite is so we can produce the molecule that is going to help kill our microorganisms, but this particular molecule is relatively unstable, and so that creates a little bit of a problem. The other thing, of course, is that we will have an increase in the hydroxide ion concentration, and that can also create a few problems in terms of changing the pH and the nature of our swimming pool. So if the concentration of hydroxide ions builds up too much, it falls outside the range that we think is safe levels, so then we have to try and neutralize it, and we neutralize it with hydrochloric acid. And the hydrochloric acid, the H+ ions that are produced, will react with the OH- ions to produce water molecules, of course, and this will decrease the concentration of the OH- ions and return the pH back to a more of a neutral range. Now we need to do this because there's a couple of potential health effects of on our swimmers if their pH is not maintained. So eyes is important. You've probably been in swimming pools which have been overchlorinated, and they can make your eyes really red and sore. Throat is also, mucous membranes can be something that is affected by pHs falling outside of these sorts of ranges, and we want to make sure that they maintain a safety. Of course, we can have too much of a good thing. If we add too much acid, then the pH will drop too far. And the problem with that is that acids and metals react, and if there's any metal fittings in the pool, then they could very easily react and corrode. So we don't want that to happen either. So when the pH is around about 7.5, then the ratio of the active hypochlorous acid to the inactive hypochlorite ion is about 1:1, and maximum chlorination efficiency is achieved. And of course, if you remember our discussion of buffers, this 1:1 ratio between the acid and the conjugate base, weak acid and the conjugate base, is exactly what we're after when we're looking for buffer solutions. So if you have a pool, then you've probably got a pool testing kit, and the testing kit is designed to continually monitor the pH and so tell you if you're falling outside of those ranges. Remember, if we're down at 6.5, then we've got something that's too acidic, it's going to start attacking our metal fittings. If we've got something that's too high, then we're going to be in trouble for health. So we want to try and make sure that we maintain a standard range, and we do that by using an indicator like phenol red. In phenol red, when the pH starts to get too low, it moves into the yellow range. This is no good, and we need to bring the pH up. If the pH is too high, over 8.4, then the indicator turns a reddy purple, and then we need to bring the pH back down again. But when the indicator is in the pink to orange range, then the pH is okay, and the acidity is fine, and the waters are good for swimming. Most of the time, with things like phenol red and pool testing kits, just like the universal indicator that you've used, you often get a card which has the colours listed on it, and you can link your test kit to that card to identify the pH and to tell you whether or not the water is at the right pH. So here's a question that's come from the 2006 HSC. It was question 23, and it was a 3-mark question. Correct swimming pool maintenance requires regular monitoring of the pH level of the water. Select the best indicator from the graph to check that the pH of the swimming pool lies within the correct range of 7 to 7.6 and justify your choice. So here's a key word here. All right, if we've just got to pick an indicator, that would be a 1-mark question, okay? There's 3 indicators here, so you've got a 1 in 3 chance of picking it correctly. But that's still only going to give you 1 mark, and that's why when we read something like justify, we're actually having to try to provide evidence for the reasons that we've chosen something. So we need something that's going to be in this range 7 to 7.6. So the first one we look at is methyl orange. And what we notice is methyl orange has its transition range between about 3 and 4.5. That means in the key region that we're looking for, which is 7 to 7.6, which is this region here, it's going to be yellow and it's going to remain yellow. And so that is not a good choice for us. If I drop down to phenolphthalein, you'll notice that its transition range is up here, so about 8.5 to 10. So in the region that we're interested in, again, the phenolphthalein is colorless all through this range. And so that's not telling us anything either. However, bromothymol blue is yellow up to a pH of 6 and becomes blue from a pH of about 7.5 onwards, which means that in this region here, it's going to be green. So it's going through a transition point around the range that's exactly corresponding to the range that we're after. So bromothymol blue is a good choice. So that's our 1 mark. Our justification is that the transition range for bromothymol blue is in the range 6 to 7.5, and that corresponds to the pH that we're looking for our swimming pool water. Okay, and the bromothymol blue will be yellow below 6, will be green between 6 and 7.5, and it will be blue above 7.5. Thanks for watching.